Thank you for attending this session. I will present you the theorem of the Keplerian kinematics and its consequences. Looking at the kinematics of the Keplerian motion, we will demonstrate here, with a theorem but no postulate, that the Newton's acceleration is the consequence of the kinematics. The classical gravitation is not a matter of attraction, but of rotation. The rotations of the galaxies can be explained without dark matter, and the Einstein's equivalence principle cannot be correct. Well, let's go. So what is the theorem of the Keplerian kinematics? The literature describes that the holograph plane representation of the Keplerian motion shows that the velocity is simply the addition of a uniform rotation velocity and a uniform translation velocity. This property is, however, always presented as a consequence of the Newton's postulates, which is always presented as prior to anything else. But now, inversely, starting from this kinematic property, can we deduce the Newton's acceleration? To investigate this, we first state this kinematic property as a theorem here. The mathematical expression of the theorem is, of course, trivial. Here is the rotation velocity, defined as this, and here is the translation velocity, defined here. Of course, the theorem will be true only if it can explain the three laws of Kepler. We will show that this is the case indeed, but first I want to show you these velocities in action on a Keplerian orbit. Here are presented both rotation and translation velocities at 4 different steps of a conic trajectory. Note that the translation velocity Vt has always the same direction and the same amplitude all along the trajectory. Also note that Vt is always perpendicular to the main axis of the ellipse. Note that the rotation velocity Vr is always perpendicular to the vector radius. Here at the periapsis, Vt and Vr have the same direction, so the resulting velocity is maximum. And at the contrary, at the apoapsis here, Vr and Vt are of opposite directions, so V is minimum. Take care. R does not stand for radial, but for rotation, and T does not stand for tangential, but for translation. So we said before that we have to prove that the theorem of the Keplerian kinematics is able to explain the three laws of Kepler. I will not present you here the complete demonstration, that is rather trivial, because of the simple mathematics of the theorem. You will find a complete demonstration with details at this address here. Well, among the important results of the calculation, we can note that the Keplerian constant here must be equal to the product of the norms of the angular momentum and the rotation velocity. The parameters of the conic defined in the first law here are given by this expression. Here is the eccentricity as a scalar and as a vector, and you can understand now why Vt is always perpendicular to the main axis of the ellipse. Here is the semilatus rectum, and note that the derivative with respect to time of the true anomaly is not equal to the frequency of rotation coming from the definition of the rotation velocity. Both are related by this relationship here. So it is rather simple to prove that the theorem explains indeed the three laws of Kepler. But the theorem teaches us some more important facts. Indeed, the theorem of the Keplerian kinematics does more than only verifying the three laws of Kepler. The derivation with respect to time of the velocity described by the theorem leads trivially to an acceleration here. And of course, this acceleration is centripetal because it comes from the rotation velocity. Furthermore, this acceleration is also nothing else but the one of Newton at the condition that LVR equals Gm. Therefore, the Newton's acceleration appears as a consequence of the kinematics, but not anymore as a predecessor. The same condition is required to make the Newton's postulate and the kinematics agree on the third law of Kepler, as we saw formerly. Note also that the theorem is consistent with the Galileo's principle of equivalence, stating that the motion in a gravitational field must be mass independent, and this is because the theorem is itself mass independent. Finally, also note that calculating the square of the velocity from the theorem, it is easy to define a massless mechanical energy fully compatible with the one described in classical mechanics. Actually, you would multiply this expression by the mass of the orbiter, you will get its classical mechanical energy. So what do the kinematics finally say about the Newton's postulates? First, the acceleration is centripetal, so the minus sign here is due to the rotation, but not to the attraction. Second, the numerator has to be LVR, but not Gm. And we have a problem here, because the kinematics are mass independent, so they cannot handle the concept of mass. Only a physics theory can do that. Without knowing it, Newton has implicitly postulated that LVR equals Jm. But a postulate is not an acceptable scientific explanation. So we need another theory of physics that will be able to explain why LVR equals Jm. Okay, from what we said before, and considering that the theorem of the Keplerian kinematics is the foundation of the gravitation, we can forecast the three laws of Kepler, forecast the Newton's acceleration, as well as the Galileo's principle of equivalence, and also the existence of the classical mechanical energy. We can even explain why the bodies are orbiting instead of collapsing by attraction. But the Newton's postulate is not able to explain why LVR equals Gm. So we need a new theory of the gravitation that can explain it. Well, let us now look at some consequences of this theorem, starting from the body falling. If you hold an object in your hand, its velocity is null, but it must nonetheless respect the theorem of the Keplerian kinematics. This means that the rotation and the translation velocities are of the same amplitude but opposite directions. The rotation velocity is provided by the gravitation, while the translation is the result of the constraints that disable the orbitation. Now let the object fall to the floor. Doing so, you will decrease the constraint applied to the object, so the translation velocity will be lowered, and consequently the eccentricity of the motion will be close but lower to 1. And this describes a very sharp ellipse. The Earth here in blue would be transparent. This is roughly the trajectory that will enter the object that you let fall. But of course, locally, from your hand to the floor, the trajectory can be approximated to a straight line. But actually, this is not a straight line. This is the part of a conic. Let us now speak about a major consequence of the theorem, concerning the rotation of the galaxies. Considering that the stars are on circular orbits inside the disk of galaxies, the third law of Kepler gives us the expression of the velocity with respect to the distance to the center of the galaxy. And for Newton, k is equal to gm. So the velocity must decrease if the distance increases. And what we should observe is this red curve here. But now, we all know that what is actually measured is this green one here. So we have a problem, of course, here. Now, for the kinematics, k is equal to Lv. So the velocity is given by this new relationship here. And to keep the velocity constant all along the distance, we also have to keep L omega constant all along the distance. And you know what? L omega has the dimension of an energy. Well, actually a massless energy as I am using it here. So the kinematics can explain the rotations of the galaxies if the stars, regardless to their distance, are populating the same massless energy level of the galaxy. This is clearly a macroscopic version of the Planck-Einstein's relation driving the atomic or molecular energy levels. So we conclude that we need a new theory of the gravitation that can explain the use of energy levels in the structure of the galaxies. Well now, you could still faithfully believe that the Newton's postulate is always true in the whole universe at all scales and conditions. You shall then add more postulates to explain the experimental measures. What about dark matter, Mond acceleration, and so on? But piling up postulates over postulates until the experiment is explained is not an acceptable method in science. One thing is sure, you cannot ignore the kinematics because they embed no postulate at all. You shall then rather consider that a new gravitation theory is needed that could explain LVR equal Gm and the validity of a macroscopic version of the Planck-Einstein relation in the structure of the galaxies. Well, this being said, we will proceed with another important consequence of the theorem. Let us now look at the gravitational acceleration versus the mechanical one. If an orbiter is thrusted by an engine, the mechanical acceleration here must add to the gravitational one here that we saw formerly. If we integrate this acceleration with respect to the time, we shall trivially get the expression of the velocity here, and of course this last must be consistent with the theorem of the Keplerian kinematic. We already know that the integration of the gravitational acceleration leads to the rotation velocity. So the integral here must be equal to the translation velocity only. And we conclude that any mechanical thrust in any direction will only change the translation velocity, but never the rotation velocity. And actually, this is quite logical, because a force must have a physical connection to the axis of rotation to cause a rotation. But the mechanical force has no connection to the central body of the Keplerian motion. At the contrary, the gravitational force has a connection to the central body. This is the gravitation itself, so it can cause a rotation. Therefore, the gravitational and the mechanical accelerations are of two different natures. The gravitational one causes the rotation, and the mechanical one can only cause a translation. So the kinematics disagree with the Einstein's equivalence principle. Let's look at some experiments that disagree with the Einstein's principle. Can we accelerate an orbiter by letting it on a circular orbit? The only way to achieve so would be to have an engine that can simulate the gravitational rotation. This engine would have the same effect on the orbiter as if the mass of the central body would have increased. With such an engine, the problem of the space rendezvous would be solved. First, go to the desired circular orbit, and then accelerate by remaining on it until you catch up the space station. That would be nice, but Buzz Aldrin, also known as Dr. Rendezvous, would explain you that this is absolutely not what happens in the real world. And this is why the problem of the space rendezvous is so complex to solve. No engine has ever been able to simulate the gravitational rotation. A circular orbit cannot be simulated by the addition of small translations as short as they could be. Any microthrust will change the characteristics of the conic as expected by the theorem, with no way at all to avoid it by controlling the rotation velocity. So the engineers are led to use the famous low-thrust trajectories. And at last we have to tell a word about the Einstein thought experiment of the observer inside an elevator. If the guy let a ball fall, he will be able to know if he is at the surface of a planet rather than thrusted by a mechanical force. On a planet, the ball will fall on a conic, while with a mechanical thrust, the ball will fall on a straight line. Well, it is time to conclude now, so let me recall the most important points. The theorem of the Keplerian kinematics is consistent with all the experimental observations, 3 laws of Kepler, mathematical structure of the Newton's acceleration, Galileo's principle of equivalence, classical mechanical energy. The Newton's acceleration appears as a consequence of the theorem. The classical gravitation causes the rotation, but not the attraction. The kinematics allows the rotation of galaxies observed experimentally at the condition that a macroscopic version of the Planck-Einstein's relation is at work. The kinematics contradicts the Einstein's equivalence principle by showing that the gravitational and the mechanical accelerations are of 2 different natures. And finally, we need a new gravitation theory that explains why LVR equals Jm and the existence of a macroscopic version of the Planck-Einstein's relation structuring the galaxies. I thank you for your attention. You can get some more physics with no postulate by googling Vixra Hervé Le Cornec. Please feel free to write to me at this address if you have any question, or to propose me a grant to help me financing my research, of course. Thank you again to all of you.